Warm welcome to all viewers. In last session, we are discussing about the chapter Simple Stresses and Strain. We have studied the behavior of the body under different conditions of loads, and the elastic bodies and the plastic bodies, they change according to the type of the loads. We also learned the mechanical properties of the materials. These are the different mechanical properties: elasticity, plasticity, ductility, brittleness, malleability, toughness, hardness, strength, fatigue and creep. So these are the different, based on these properties we can clearly study the behavior of different materials with the different properties under the condition of external load, or when they are subjected to external load. So these are some of the properties we studied in the last class: toughness, hardness, strength, fatigue, creep, loads and forces also we studied, and different types of forces: compression, tension, torsion, bending. So these are the different forces. These are the examples: what is compressive force, what is tensile force, shear force. Okay. And what is a stress? Stress is applied force by cross sectional area. And what is a unit? Unit of a stress is Newton per mm square, or Newton per meter square, or kilonewton per meter square. Here 1 Newton per meter square is equal to 1 Pascal or 1 Pa. And when the large quantities are to be measured, 1 kilo is equal to 10 raised to 3 kilonewton kilo, 10 raised to 6 is mega, 10 raised to 9 is giga, 10 raised to 12 is tera. So we also learned how to convert those units to the larger quantities. These are the types of stresses: tensile, compressive, shearing, bearing, bending stresses. So we learned these, some of the examples of tensile stresses. After studying the stress, the important part of this chapter is strain. Stress is the force of resistance present in the body that will show against the external force. That is, the stress is nothing but an internal force, or the force of a resistance, that is called as a stress. Now strain. When a body is subjected to external load, there will be a change in the dimension of the body. A geometrical measure, strain is a geometrical measure of a deformation representing the relative displacement between the particle in the body. We can observe there is when any body of a mechanical property, particular mechanical property, it changes its dimensions. See how it will be. Between the particles there is a displacement which we can observe through eyes, or internally there will be a displacement of the particle. So there we can observe there is a increase in length or decrease in length, increase in volume, decrease in volume. So even in the lateral dimension, breadth or depth. So the majorly difference between the stress and strain is: stress is the internal force or force of resistance. Strain, when the body is subjected to external load, there will be a change in the dimension of the body, maybe laterally or longitudinally. So as I told you, it's a geometrical measure which measure the displacement of the particles. As I told you in the stress is denoted by sigma, but here it is strain is denoted by epsilon or small e. For each and everything we have a denominations. Strain. So again repeating, strain is a change in length or dimension or deformation divided by the original length or dimension. So change in length we represent it by dl, and the original length is L. So as I told you, here the original length of rod is L, and when it is subjected to a load, uniaxially loaded rod, see the force equivalent opposite moving outside, and we can call it as a tensile stress or a tensile force which is moving away from the force of direction. Now the original length L changed to delta L. So you can see the change in length. So you can represent it as I told you, epsilon E or small e is equal to delta by L, change in length by original length. Types of strains: tensile strain, compressive strain, shearing strain, volumetric strain. It is same as in the stress. In stress it is tensile stress, here it is tensile strain. In the stress it is a compressive stress, here it is compressive strain. Shearing stress, shearing strain. Volumetric stress, volumetric strain, or the bearing stress. Whole as a here there is no volumetric stress there, it will be only volumetric strain in the types of strain. What is a tensile strain? As I told you, tensile strain or tension is a strain which leads to the expansion. There is a pull, the force is for pull in the direction of force. The length of material tends to increase in the tensile direction. Body is subjected to two equal and opposite pulls. Here tensile is pull, compression is push. So therefore tensile strain can be further defined as the change in length and the original divided by the original length. The main basic definition of strain, it is going to continue with all the types of strains. As the strain defines the change in length divided by original length, and formula also remains to be same, epsilon is equal to delta L divided by L. Example, tensile force. You can observe two equal force acting in opposite direction in the direction of force, and the original length L0 changes to delta L plus the L0. So therefore, as I told you, again strain is the original length, change in length divided by original length. So that is elongation divided by original length, delta L by L0. Compressive strain. What is the compressive strain? Compressive strain on a material which leads to the smaller value. If you take a tensile strain, there it leads to elongation or expansion. Compression, it leads to the smaller dimension, it compresses. Okay, when a body is subjected to two equal and opposite pushes, there it is, you can observe here, it is pull. You can observe here in this tensile strain, pull, and when you come to the compressive strain, here it is push, causing the shortening in the direction of force. There in the tensile, causing the expansion or increase in length. So therefore compressive strain is equal to change in length divided by the original length. Again the basic definition of a strain. Therefore strain is defined as epsilon equal to delta L by L. Example of it, two equal forces acting to the direction of the force or inside towards the body, and you can observe two equal and opposite forces acting towards or pushes. There in tension it is acting away, pull. Here it is push, acting towards, and which leads to the shortening of the body or shortening of the volume. So that is called as a compressive strain. Here in strain we are measuring the only geometrical value, and strain doesn't have any unit. So when you divide change in length by original length, or the length units get cancelled, and strain is going to be the constant value and it doesn't have any units for it. Whereas stress, the unit of stress is Newton per mm square, load by area, Newton per mm square. Strain is change in length divided by original length, no unit. See the other example of it, strain, original length, extension, it is a tensile strain, you can observe it, original length, extension. See that? You can observe the change in the lateral dimension. See the compressive strain shortening, the forces are towards, here the forces are away. Shortening of the length, and the amount of shortening is represented by delta. So that is, those are the difference between tensile strain and compressive strain. And lastly and importantly, this is the example of a shear strain. What is a shear strain? Shear strain is the transverse displacement when load is acting parallel to the or tangential to the surface of the body. There is a transverse displacement, so the strain is given by transverse displacement divided by the distance between the upper and lower faces. Here you can observe, you can see here A, B, C, D when is subjected to load P, D will shift to D dash or D1 delta dash or the delta L. You can see here of length L, the change in length on the top of surface, that is a shear strain with a phi angle of depth h. Now the body, when the force is acting parallel to the surface of the body or acting tangential to the surface of the body, it gets shifted to delta L. So therefore you can observe here transverse displacement d1 divided by AD. What is d1 here in the diagram? d1 is delta L d1 divided by, what is the displacement length? AD. What is the original length here? This is AD. AD dd divided by AD. So delta L divided by h. What is AD? AD is h. So therefore observe carefully, shear strain is phi is equal to delta L divided by h. Phi is equal to a small, since tan phi is very small, we consider only a phi value. So after studying a stress and a strain, stress is load by area, strain is change in length by original length, that is P by A. For stress, sigma is equal to P by A, and for strain, epsilon or small a is equal to change in length by original length. So therefore after studying these two, Hooke's law, it states that within the elastic limit, stress is directly proportional to strain. What is Hooke's law? Hooke's law is stress is directly proportional to strain under the condition of elastic limit. When the material is in elastic limit, stress is going to be proportional to the strain. So that is, stress is directly proportional to strain, or stress by strain is equal to constant. So this constant, stress by strain, after removing this proportional quantity, then we can write it as stress by strain is equal to constant. So the above constant is known as coefficient of elasticity or modulus of elasticity. What is this constant known as? This constant is known as coefficient of elasticity and modulus of elasticity. This we are going to study further it as Young's modulus. Let us see in the next slide. So these are some of the elastic quantities: Young's modulus E, rigidity modulus C or G or N, and bulk modulus K. And the unit of all the elastic quantities, that is Young's modulus, bulk modulus, rigidity of modulus of rigidity or rigidity modulus, the unit of these elastic constants will be Newton per mm square. First one, Young's modulus. It is the ratio between tensile stress by tensile strain, or it is the ratio between the compressive stress by compressive strain. So therefore, as we studied in the Hooke's law, the coefficient of elasticity, where the constant value coefficient of elasticity or modulus of elasticity is also known as Young's modulus. So here we studied Hooke's law. What is Hooke's law? Stress is proportional to strain, and when you remove that you get a constant, and that constant quantity is known as coefficient of elasticity. The same elastic quantity or the modulus of elasticity we call it as Young's modulus. So it is represented by E, capital E. So what is the value? Stress by strain. Stress is sigma, epsilon or E is strain. So therefore, as I told you earlier, tensile stress by tensile strain or compressive stress by compressive strain. It is also called as a coefficient of elasticity or modulus of elasticity. Next, rigidity modulus, C, it is represented by C or G or N. It is the ratio between shear stress to shear strain. So again it obeys the Hooke's law, stress by strain, but rigidity always connected with or related with only shear values. Remember, rigidity means shear, you have to remember like that. It is a ratio between the shear stress and shear strain. It is also known as modulus of rigidity. So therefore, modulus of rigidity C is represented by shear stress by shear strain. And the last one of the last quantity, the bulk modulus of elastic constants. It is a ratio of direct stress to volumetric stress, volumetric strain. Remember, the first and second quantity, that is Young's modulus, only stress by strain. Here in the bulk modulus, it is stress by volumetric strain. See, bulk means volume. You have to remember like this. Rigidity means shear, and Young's modulus means you have to relate with Hooke's law. Young's modulus is tensile stress by tensile strain. Rigidity modulus is shear stress by shear strain. Bulk modulus means direct stress by bulk means volumetric strain. So therefore, bulk modulus K is equal to stress divided by volumetric strain. Now we will study about the calculation of extension or elongation and shortening of bar. How this we are going to we'll learn how to calculate these quantities mathematically. So as in the first diagram, as I told you, in the strain, original length divided by change in length divided by original length, epsilon is equal to delta by L. So we can observe the other diagram. Here it is elongation or extension of bar, you can see in this diagram. Now in this, what is this? Shortening of the bar, that is compressive. Elongation, tensile. You can see the change in length, that we should observe carefully. Extension or elongation and shortening of bar. When bar is subjected to tensile load, it elongates by delta L. When bar is subjected to compressive load, it shortens by delta L. We know that stress is equal to applied load by cross sectional area, that is P by A, and strain epsilon or small e is equal to delta L by L. Stress is equal to change in length by original length, and from Hooke's law and Young's modulus we know that stress by strain is equal to constant. So as you know that stress by strain is equal to constant, and E is equal to, you can observe here, sigma by small e or epsilon. So we know that sigma is equal to, what is sigma? Stress is equal to load by area. See here, P by area and delta L by L. Observe here, E is equal to P by A divided by delta L by L. Substitute the values of stress and strain here, and by calculating or equating LHS and RHS, we can calculate the change in length or elongation or extension, or what we call the shortening, extension, elongation or shortening of the bar delta L. We'll try to solve some of the problems based on this. And the important part of this, the graphical representation of a stress strain curve. It is also called as stress strain curve. We represent the behavior of the particular material, and it is represented graphically. Along x-axis it is strain, along y-axis it is stress, and we will study the different materials and their behavior, and we represent them in graphically. See here, there are points. It starts with O, A, B, C, D, E, F. There are totally 6 points. There are 6 points where the behavior of the material or the mechanical property or properties exist here. Now, we will analyze this. When a mild steel subjected to stress or a load, how it can be represented in the stress strain curve. Initially, that is, you take OA. OA, it is proportional to stress and strain. So as I told you, what is Hooke's law? Hooke's law is stress is directly proportional to strain, OA. Okay, so here we can see the straight line, and this straight line represent the elastic limit, where when the load is suddenly removed, the material regains its original shape. That is, OA is, again I am repeating, it is the portion where the material is under elastic limit and it obeys Hooke's law. Stress is directly proportional to strain. It is a straight line. And after that, the portion AB, you can see here, the portion AB, stress will be the stress will be decreased, that is, load will be decreased, and you can observe the strain continues to increase. So we start removing the loading factor gradually. Here it starts with the point A, and the load is removed gradually up to point B, and here also the stress, the body tries to elongate. That means the point B is called as yield point. You can observe here point B is yield point. There you can observe in the portion BC, it is almost parallel to the line OX, and at that point, at point B to C, there is no stress. Stress is almost nil here. You can see here stress is 0. Initially they are proportional to each other, and in portion AB the stress is a little bit decreasing, and at point from point B to C, that is portion BC, PC is parallel to OX. You can observe here, and the particular material, that is mild steel, it started yielding. Then after that, after C to D, you can see here there is ultimate load. Then the load is applied again, and the portion here that is proportional to strain, and you can observe there is an increase in load and metal continue to yield, and at point D to E, the load is the particular material, it stops taking the load. Here you can observe portion D to E. You can observe D to E again, almost it is parallel to OX. Though the load is applied, the particular material fails to take the load, and when the ultimate load, that is a stress, ultimate load is applied, that is point E, then the material, we can observe in the material there is a crack or a fracture in the material, and point F, that is ultimate load condition, point F, the material breaks down, that is called as a breaking point. Let us study in detail of that curve. It's a very important graph or graphical representation of stress strain curve. Now there are how many points are there? A, B, C, E, A, B, C, D. D is not much a major point. It's not a major point. E, F. See at point A, portion OA, the line is straight, and stress is directly proportional to strain. It obeys a Hooke's law, and as I told you, it is under elastic limit and can regain its shape. Upper yield point, point B, okay, it's a point where the middle starts yielding. You can see the graphical representation. At this point, the middle starts yielding, and strain increases, load decreases. Load means stress decreases, and BC portion almost parallel to the line OX. OX means horizontal line OX. Now point C, yield continues and material behaves like a ductile material. See here in this portion, CD portion, the material starts behaving like a ductile portion, ductile material, CD portion, and stress remains same and strain increases, and ultimate stress point, that is E. See here E, that is, this point is known as the ultimate point. Stress is maximum at this point. Ultimate stress, it is also known as ultimate stress, and bar or the mild steel elongates. Stress decreases after this point. Observe carefully here. After point E, the stress starts decreasing and strain continues to increase, and the point F, it is called as breaking point, where the bar fractures or specimen fails. So these are the important points of stress strain curve for the mild steel. So similarly we have other representations, we will study later part. So as I told you, ultimate load, ultimate stress point, what is E? Ultimate stress point E, that is in the graph, it is the maximum point. At this point, how the body behaves? Necking of the specimen, the body will be of this kind. Instead of straight, you can see the neck of the specimen, necking of the specimen at E, and point F, as I told you, it is a breaking point where the fracture occurs or the specimen fails. Stress by strain diagram for the different materials: high carbon steel, nickel chrome steel, mild steel, wrought iron, cast iron, copper, cast iron, cast aluminum. You can observe the three, high carbon, nickel and mild. It behaves like the mild steel graphical representations, where you can see all the points A to B, B to C and C to D. You can observe almost all the points, that is yield point, ultimate points. So almost it looks similar to that kind of a mild steel. We studied about a mild steel. Wrought iron, where it suddenly it behaves like a brittle type. Cast iron, copper, ductile material, cast aluminum. So these are the different representations of common materials when they are represented graphically, stress by strain. So these are the values. As I told you, stress always represented in the form of percentage and it doesn't have any unit. Stress, it is represented with a unit in Newton per mm square. You can observe the values of that. Similarly, aluminum alloy, and it is basically a ductile material. Here initially up to this point it behaves, that is stress is directly proportional to strain, then strain stops, the load stops, and the body, the behavior of the body continues to elongate. It never breaks here. It behaves like a ductile material. There is no fracture point and it continues to elongate. Similarly, the stress strain diagram of hard and soft rubber. Hard rubber, we can see somewhere the breaking point or the ultimate point, and soft rubber, it tries to take the load up to certain limits, but you can see the strain, it continues to change its shape despite of the stress. Here the stress is very less, but strain, it keeps on increasing. Soft rubber, hard rubber, some ultimate breaking point is there for this. For cast iron, as I told in the main graph, here it is cast iron. See, there is, it looks to be almost proportion, so it is almost proportional to stress by strain. That means it is under the limit of elasticity. So till now we have studied the majorly stress and strain. The stress formula is equal to load by area, strain is equal to change in length by original length. Hooke's law is stress by strain, and Young's modulus, rigidity modulus, and bulk modulus. So let us try to solve some of the problems related on those formulae. So as I told you, sigma is stress P by A applied load divided by cross sectional area, epsilon or E is equal to strain, it is change in length divided by original length. Original length. So what is Hooke's law or Young's modulus? Capital E is equal to stress by strain. This you have to remember while solving the mathematical problems and errors also. What's the first question here? A steel bar of 2 meter long, let us write the given data. A steel bar of 2 meter long, 150 mm square cross sectional area is subjected to an axial pull. Pull means what is that? It is a tension of 15 kilonewton load. Find the elongation of the bar given capital E is equal to 200 GPa. What is capital E? Capital A is Young's modulus. So now we'll write the given data. Length L is equal to 2 meter. So we try to convert these main units to smaller units for easier solution of the problem. 2000 mm. Cross sectional area, small, I can write it capital A, it is 150 mm square. So convert those meter values into mm values, convert the kilonewton values to Newton values. So axial pull, it is a tension P, what is that? 15 kilonewton. As I told you, it can be written as 10 raised to 3 Newton, because 1 kilonewton is equal to 10 raised to 3 Newton. And what is E? Young's modulus E is equal to 200 GPa. As earlier I told you, GPa, what is GPa? 1 Pascal is equal to 1 Newton per meter square. 1 GPa equal to how much? G means 10 raised to giga 9, 10 Newton per meter square. So for K it is 10 raised to 3, for M it is 10 raised to 6, for G it is 10 raised to 9, for tera it is 10 raised to 12. So as I told you, 1 GP is equal to 10 raised to 9 Newton per meter square. We want this particular Young's modulus in the form of Newton per mm squares. So let us convert this Newton per meter square into Newton per mm square. Now I will write this 10 raised to 9 divided by 10 raised to 9 Newton divided by 10 raised to 3 mm into 10 raised to 3 mm. So I am converting this meter into mm, mm into mm, meter into meter or mm into mm. So at last I will get the value of GPa 10 raised to 3 Newton per mm square. What is the value of E here? One GPa. So 200 into 10 raised to 3 Newton per mm square. 1 GPa means how much? 10 raised to 3 Newton per mm square. Now what do you have to find? Find the elongation of the bar. Given that L, area, load, Young's modulus, we have to solve or we have to find the unknown value of bar, that is elongation of bar. So as we know that elongation is the term which is related with strain. So we know that what you have to find? We have to find delta L. So we know that strain equal to E equal to, we'll write it E only, delta L by L. So we have to find this. Okay. So now we have to calculate delta L. To calculate L, we should know the strain value and we should know the L. L is already given. So to calculate this E or the strain, we know the relation Young's modulus E equal to stress by strain. So what is this stress? Stress is P by A, strain is dl by L. So first let us calculate the value of stress sigma. Sigma is equal to P by A. What is P by A? P is what? 15 into 10 raised to 3 Newton divided by area 150 mm square. What is the value of stress? 110 Newton per mm square. So now we know that stress by strain is Young's modulus. Therefore, substituting this value in the equation number 1, so substitute the value E is equal to sigma is 110 Newton per mm square. E we don't know and we know capital E, that is Young's modulus, how much? 200 into 10 raised to 3 Newton per mm square. So after calculating E, we will get a value of E is equal to, small e is equal to 5 into 10 raised to 4. Remember, it doesn't have any units. So after finding small e, we can calculate the delta L, change in length. Small e is equal to delta L by L. So therefore delta L is equal to E into L, that is 5 into 10 raised to minus 4 into, what is that? L is 2 meter long, that is 2000 mm, and therefore change in length we can calculate equal to 1 mm. Or we can directly calculate delta L, that is Young's modulus is equal to stress by strain P by A divided by delta L by L. If you cross multiply that, PL divided by delta L into A. So therefore we can remember to calculate this, PL is equal to A into E, which you have learnt in the other session. Delta L is equal to P into L divided by A E. So I'll repeat the problem once again. It's axial pull P when subjected to load of 15 kilonewton of cross sectional area 150 mm square. Here the aim of the problem is to find the elongation of the bar given the Young's modulus E is equal to 200 GPa, and you have to remember to convert that GPa to Newton per mm square. 1 GPa is equal to 10 raised to 9 Newton per meter square, and Newton per meter square is again converted into Newton per mm square, and at last we get 1 GPa is equal to 10 raised to 3 Newton per mm square, and 1 MPa equal to, we get 1 Newton per mm square. So these two you have to remember while solving the problem. 1 MPa is equal to 1 Newton per mm square, 1 GPa is equal to 10 raised to 3 Newton per mm square. Now let us work out the second problem. Alloy bar of 1 meter long and 20 mm by 10 mm cross section is subjected to compressive load. There it was tensile load, here it is compressive load of 20 kilonewton. If the modulus of elasticity is equal to 100 GPa, find the change in length. As I told you, the compressive load, alloy bar of length 1 meter of the cross section 20 mm by 10 mm subjected to compressive load. Compressive load means the load is in the direction of force towards, it is push. Compressive means push, tensile is pull. How much load? 20 kilonewton. Given E is equal to 100 GPa. As I told you, 1 GPa is equal to how much? 10 raised to 3 Newton per mm square. We will write the given data. just write the given data carefully. Length L is equal to 1 meter long, that you convert into mm, it will be 1000 mm. Now area A is equal to 20 mm into 10 mm is equal to 200 mm square. Load P (20 kilonewton), 20 into 10 raised to 3 Newton, and Young's modulus E equal to, let's write this value, 100 into 10 raised to 3 Newton per mm square. What to find? To find delta L. We know that, as we simplified in the slideshow, delta L can be calculated using the formula P by L into A into E. P is a load, L is a length, A is a cross sectional area, is a Young's modulus. These are the known values. What is the P here? 20 into 10 raised to 3 Newton, length 1000 mm, cross sectional area 200 mm square, Young's modulus 100 into 10 raised to 3 Newton per mm square. Newton get cancels, mm square get cancels, so we remain with the value mm. The unit of change in length delta L is equal to mm. After simplifying delta L, we get delta L as 1 mm. That is, when bar is subjected to compressive load, the bar shortens by 1 mm. This is delta L. This is original length P. So change in length, here it is shortening of the bar. Tensile, it is elongation of the bar. So in this type of problem, we learn to calculate the change in length under compressive load and in tensile load. Now we take up the different type. A straight bar of 500 mm length with the cross sectional area 500 mm square. Find the magnitude of compressive load. Which is decreased by 0.2 mm and E is equal to 200 GPa. A straight bar of length 500 mm subjected to compressive load, and it changes its dimension or shortens how much? 0.2 mm, that is delta L, here in this type we have to calculate the value of P. Earlier we have calculated the value of delta L. Now delta L is given, we have to calculate the P, force P. So what is the given data here? Here we have to find P. So length L is equal to 500 mm and P you have to find, area is equal to 500 mm square. As I told you, E is equal to 200 GPa or 200 into 10 raised to 3 Newton per mm square. See, all the units are in the form of Newton per mm square, Newton or mm square. Now we have to calculate the P. So delta L is equal to, we know that delta L is equal to P into L divided by A into E. So we know this, we know the delta L, we know the length, we know the area, we know Young's modulus. We have to calculate P. P is equal to the value of delta L, we know, no, area into capital E divided by L, and after substituting the values of delta, area is 500 mm square, Young's modulus 200 into 10 raised to 3 Newton per mm square. So L is equal to 500 mm and we can calculate, we will get P is equal to 40,000 Newton or 40 kilo Newton. That is, the compressive force P is equal to 40 kilonewton. So for given any problem, there will be one unknown value. With that, convert the units in the form of Newton, kilonewton to Newton, meter to mm square, and if we remember this formula, that is PL by, that is using this relation we can calculate any unknown. Whereas quickly we will solve one more problem. A steel rod 25 mm dia, 4 meter long, subjected to axial pull 40 kilonewton. Find what you have to find: stress, strain and Young's modulus. So we know that P sigma is equal to P by A, stress E is equal to dl by L, and Young's modulus. So Young's modulus is given, we have to find the elongation. Young's modulus is equal to 2 into 10 raised to 2.10 raised to 6 Newton per mm square. 2.1 into 10 raised to 5. So substitute the values of P here, area, and calculate the stress. Substitute the value of substitute the value of these stress and strain in the relation sigma is equal to E. Find E is equal to sigma divided by capital E, as you have done in the first problem, and with that E calculate dl by L, or directly use, we can use the formula delta L is equal to PL divided by AE. So remember, to calculate the unknown values P or area or the Young's modulus, use this relation, and K should be taken to convert the units, that is kilonewton to Newton, meter to meter square, gigapascal to Newton per mm square, megapascal to Newton per mm square, and remember the relations. So next class we try to learn about the composite bus and elongation of bus. Thank you.